Thank you, Jamie, and thank you to Laura and Sheila. Working on the project with me is Dr. Praveen Saxena. He's away lecturing in India right now, and Mukund Shukla, who I will introduce shortly, will be giving the second half of the presentation. So, as a broad overall objective, we're looking at selection of novel varieties and development of integrated plant production systems through tissue culture and mechanisms to enhance the early stage survival of transplants coming out of the tissue culture process. Specifically, we're looking at using native species, and these are plants that are native to northern US and Canada, to develop novel germplasm that's adapted to drought and low nutrient environments. We've heard other talks about low water, and certainly we've talked about nutrients. And so that's one of the founding principles of the breeding program. In the other three specific objectives, those are developing tissue culture systems to for the rapid propagation of high quality, disease-free plants. This includes optimizing light quantity and light quality, use of plant growth regulators, and different tissue culture vessels and bioreactors for improving in vitro propagation. Along with that, GRIP, the Gosling Research Institute in Plant Preservation, is developing cryopreservation techniques to preserve important genotypes and rare ecotypes that might be endangered. And we're using this to, we're using cryopreservation to preserve important ornamental species. Okay. One of the other things that we do is we run trial gardens at 3 locations, Guelph, Milton, and Royal Botanical Gardens, as a sort of an outreach. But in these trial gardens, we're hosting the newest releases from breeders from all over North America, and we also have a perennial trial. We host 2 to 3 open houses over the course of the season. In 2022, we had 200 plus visitors from industry, the landscape trades, and the public. Okay. At the Milton site, we also ran a pollinator trial with Sarah Jandrovicic, basically to look at how attractive some of our non-native species were to native pollinators. And I can say that that they are attracted to non-native plants. So here's just a general shot of our trial gardens. These are non-replicated trials, but they're large enough that it gives people looking at them a true sense of how the plants perform in the Guelph environment and also at Milton. Okay. At Milton, we're also running a container trial, and at Milton we also have a perennial trial, recognizing that perennials are a very important part of the gardening process. Okay, our trial gardens are open, especially the one at Guelph is open sort of 7 days a week. And so people can come view the selections, and they're all well labeled, so they can get an idea of how these plants grow in this specific environment. We see Roger Shantz on the right here, who does a lot of the technical support for the program and runs the trial gardens for us. He's just giving a sort of a preamble to this group as they start to look at the gardens. We provide feedback to the breeders about the performance in this specific location and the Milton location, of course, so that they can make their judgment as to what's going to go forward for commercialization. Okay. We work with many species in the breeding program. And as I mentioned, these are Canadian species, Canadian native species. The reason for doing that is these are already existing in nature, and they've survived in a variety of climates and have done quite well. So it's a natural place to start. I won't say much about the breeding program other than it's a recurrent selection program that deals with populations, and the advantage of that is that from these populations we can pull out selections or elite individuals and then put them into we can do further crosses, or we can put them into a testing program and test them at a place like the trial gardens. Okay, I'm just going to skip that. In each of the cases with these species, we have breeding populations that are going through cycles of selection, and as we see valuable plants, we pull those out either for further crossing or testing. And this is just a list of some of the species that we're working with, and you'll see some of these in a couple of minutes. In order to achieve the tolerance that we want and produce resilient plants, we screen in the greenhouse. We screen for two things: low nutrients, three things really: low nutrients, but drought and salt tolerance. And here we are immersing plants in a saline solution, and we do that. Some of the details here: we just take 50 cell trays, immerse them in a weak salt solution, and then after a period of time, we take the best performing plants. And this, I mentioned that we do this for salt. We also do it for drought. We take the best performing plants, and they become the parents for the next cycle of selection. And we achieve that through just intercrossing these plants. We may move them to the field in Elora, make our selections from there for the next generation. Okay. We use the field site at Elora for testing. And I want to point out that in 2022, in many ways, it was a terrible year because of lack of water, but it was a great year for these plants. Basically, we had no or almost no rainfall from late June through July and into late August. And this is the kind of vigor that we saw with these plants. So they are clearly adapted to a drought environment. And this is also growth with no fertilizer. Okay, I just want to highlight a couple of the plants that we're going to move forward with. This is Aquilegia, or Eastern Red Columbine. Although this picture is from the greenhouse, I wanted to show you the flower. In the field, it has very vigorous growth, high fruit flower number, very attractive color. It's certainly winter hardy and is drought tolerant. So a good candidate for advancement. Okay, this is Helenium. It's a late season bloomer. It's a great fall specimen. Has a very attractive flower. This flower happens to be yellow with a slight red tinge to it. Very vigorous growth. It's drought tolerant, high flower number, and has a very long flowering period. I kept returning to the field thinking that the flowering would be done, yet it just continued on and on. So we'll move forward with this one. We've been working with 3 Liatris species. This is one of them. You'll know Liatris as it's common, another species, which I'll show in a minute, is commonly used for cut flower arrangements. In the field, this has moderate height, has a very long flowering period. Between the species, there's the color is the same, but there's a variation in flower morphology. And I'm a bit surprised that people haven't picked this up. They're clearly drought tolerant, and I believe they have potential for cut flowers. Okay. This is the other species of Liatris that you will see in cut flowers. I think it's spicata. Okay. This is Carota. It's very similar to Queen Anne's lace. It has very moderate height, a long flowering period. Again, drought tolerant. This will have the taproot that's characteristic of Carrata. And I just like to use the phrase that it has a delicate presence in the garden setting. Unlike the Queen Anne's lace, which has a white flower, you'll notice that this one has a bit of tinge of red to it. Okay. And I put these in just to show you that we went to the field sort of in August, harvested specimens of what were there, and then we had a professional flower arranger took what we gave her and made these arrangements from them, which I think are fairly attractive. I'm not saying that all of these flowers will become, all these species could be used in a cut flower situation, but it certainly shows the potential. Okay. In terms of future, we have populations of all of these species that we can continue to work with and go forward. I think the most relevant point is we plan to propagate selections of many of these species, go into wide area testing, more concentrated testing at Aurora, Milton, and find sites in Western and Eastern Canada. We're also looking at new species that, such as giant trillium and lupins, that we might work with in the future. I'm going to stop sharing and introduce Dr. Mukund Shukla. Mukund has been with the program over these 5 years. He started out as a postdoc with us, but I'm very pleased to say that he's now a research scientist in our department, and he's also curator of the cryobank, and he's been very valuable in bringing his expertise to this project. Dr. Saxena sends his apologies for not being here, but he's on a lecture tour in India. So Mukund, I will turn it over to you.
Okay, thank you very much. So I'm going to continue the presentation for our outcome for the second part of the projects, mainly the remaining objectives. So as Dr. mentioned about the GRIP like mainly focusing on to saving the endangered and threatened plant species using our biotechnological approach, mainly two major components like a micropropagation and cryopreservation. So our model is we consider as a CPR, like a conservation, propagation, and redistribution. So we are using micropropagation for mass production and preservation through the cryopreservation. So same approaches we are applying in the current project, like for the ornamentals. So before moving forward, I would like to introduce a word like what is micropropagation. So in a layman, we can say it's a vegetative propagation at micro level under the sterile control environment condition. It's basically mass production of two type plants from culture cell, tissue, and organ. And there are several advantages of micropropagation, but considering today's talk, I'm just highlighting the major advantage, like all plants coming from the micropropagation are uniform, disease-free. So, and we can produce year-round, and that we can send export the plant material across the border without any restriction. So there are several ways to do the micropropagation, and also micropropagation protocol optimization is also very specific, like a plant species specific. So we are mainly focusing on the temporary immersion bioreactor-based system that can be useful at a commercial scale. So we are just going to explain this, what is the temporary immersion bioreactor system, citing the example of chrysanthemum propagation. So you can see from this video clip that the rocker is moving and the culture vessels have the liquid medium that floating from one end to other end. So the plant material not remain all the time into the liquid medium. So they're floating all around, the liquid flow smoothly going from one end to other end. And that helps to better shoot multiplication and the remaining plant growth development. So we optimize the efficient protocol for chrysanthemum using 2 different cultivars and compared to the semi-solid culture system. So in order to optimize the light spectrum and intensity, we develop another prototype, as you can see from this picture. So there are 6 different nodes, like we can control like red, blue, green, ultraviolet, UV, in general white light. So we can control, we can make the program according to the optimization requirement. And the main feature for this rocker is the light remain very consistent throughout the culture period. Like when this movement is synchronized with the rocker movement. So the lights remain very consistent, so we can easily optimize the light condition. This is the main factor for the plant growth. So as I mentioned, like we optimize the micropropagation protocol from varieties of the plants. Each and every plant specific needs to be optimized based on the plant growth hormones requirement, culture conditions, vessels, liquid versus semi-solid, whatever. So you can see the list of the all plant species we use, and there are several other plant species. Currently, we are optimizing the protocol for the micropropagation, including the greenhouse acclimatization. So I'm emphasizing more like currently like orchid is very popular in the market. So we like also established the protocol for the micropropagation using different types of orchid, and we successfully transfer them in our greenhouse condition. Not only they are established well in the greenhouse condition, but also flower well in our greenhouse condition as well. Another point, like we are working with the local cancer group, like organized by the Six Nation group. The main purpose to bring the awareness of our technology to in their community, and we are interested. They are interested to bring more plant material for the field distribution. So we got nearly 6 different native ornamental plant species from them. We initiated the cultures using their limited plant material. We established the like a large-scale micropropagation protocol using, you can see there is a specialized one-time use cultural vessels that we can use for the optimization for the micropropagation protocol. And later we were able to transfer them in a greenhouse condition. We also optimized the condition for the greenhouse, including like soil mixtures, nutrients, like supplements, light condition. So we precondition and we shortened the time for the acclimatization. And last summer, nearly 400, 500 plants of each plant species, we transfer them over close to the Brantford area in their field condition, and almost all survive very well during the last summer season. Another major component is cryopreservation. We are using for the preserving the important germplasm. So the cryopreservation, like putting the tissue in the liquid nitrogen that have temperature around 196 degrees Celsius. So we can store the plant material for indefinite of time, because most of the all metabolic processes will freeze. So here you can see that these are general steps for the cryopreservation procedure. Right from the lax plant, we need to pre-treat before plunging into the liquid nitrogen, and after liquid nitrogen, we are reviving plants from our cryobank, culturing back in for the regrowth. So these are the general steps, but we need to optimize based on the plant species. So here is another, again, I'm citing the example of chrysanthemum. You can see the stepwise cryopreservation protocol. I'm not going in detail, but just highlighting the few points. Like explant size is very important for the cryopreservation. As you see, like the smaller size of the explant, more chance of getting the survival and regrowth. We use 2 millimeter in length for the chrysanthemum shoot tips. We use like there are standard plant vitrification solution. We modified a little bit based on the plant species. We use this droplet vitrification method, the droplet that covers the meristem tissue when we plunge into the liquid nitrogen. And same way, we need to revive from the cryobank. So that's another critical procedure to rewarm and then reculture back into the normal growth, plant growth and development. So when we do the cryopreservation, we have another advantage when we are we are able to eliminate the viruses. So that we call cryotherapy. So mainly like a cryopreservation versus cryotherapy is more almost same steps, but we are more focusing towards the smaller size of the explants and other cryoprotection solution that can help some better regrowth and survival. So that can, like, because of the smaller size, the virus load can be less and we can be easily eliminated. So you can see from this data, like explant size 1 millimeter or 2 millimeter, we are able to successfully regrow from like 40 to 50%. So that is enough because we have optimized protocol for regeneration through the micropropagation. So once we have the clean plant material, we can use our optimized protocol for the multiplication. So, so most of the time we are using the apical meristem tissue to preserve the plant material. But like sometimes if we have limited meristem tissue, so how we can preserve, so we try with the different plant parts. Like in case of African violet, we use the petioles and leaf segments. So first we optimize the protocol, like a regeneration protocol from the leaf segments as well as from the petioles. Also from the somatic amerogenesis is another kind of plant regeneration. So we are able to preserve the petioles as well as the leaf segments in liquid nitrogen, and we were able to revive from our cryobank. You can see these fully grown plants coming from the cryopreservation protocol. So based on this data, you can see as we compare the explant size, small, medium, large. Smaller is around 0.5 millimeter and larger is around 2 millimeter. And we expose the different time for the vitrification solution. So you can see that we are able to regrow from 20 to 43%. So like it depends upon the objective. If you want to just to preserve, we can use the larger size of the explant to have higher regrowth. But just in case if your objective is for the virus elimination, we can go for the smaller explant, even though have less percent of regrowth. But we can, that again I mentioned earlier, we can regrow the plant material, clean material using the micropropagation protocol. So through this like a micropropagation and cryopreservation, we are integrating all different type of factors, right from the initiation, selection of the plant material, selection of plant growth hormones, light conditions, temperatures, culture vessels, culture system. So we call as like an integrated plant production system for the production of mass production of the any interested plant species. So basically we are able to develop a complete system for commercial production of pathogen-free stock plant material that can be delivered locally and easily available to the nursery or growers. And on the other hand, we can preserve all genetics potential breeding line or any identified new line can be preserved in our current cryobank. So just I want to cite like one of our industry partner, Upper Canada growers develop a larger tissue culture lab, maybe largest in Canada, and they are able to produce currently fruit trees and grapevine. So similar way, they can any ornamental plant species can be multiplied over there for a larger scale and can easily be distributed locally. So this is the one just how we can move for the commercial scale. Now, thank you very much. I would like to again back to Dr. Sullivan to summarize the talk.
I just want to thank you, Mukund. I just wanted to acknowledge all the people that worked on the project. Roger Shantz providing technical support to the program, Bob Nichols providing lab support, and a host of other people who are experts in tissue culture and cryopreservation. So Jamie, thank you very much. And thank you to all of our sponsors.